At the beginning of the Industrial Revolution, most of the manufacturing world was powered directly by water. Any industry needing power had to be located along the banks of a river or stream, or the course of the river had to be diverted to reach the plant. It was the Welsh who first employed steam power in industry to operate the great mine pumps that lifted standing water from working mines. Steam soon became the world's most popular power source, chiefly because it could be produced cheaply and transported easily to one or several workstations. Steam has provided power to drive engines, turn turbines, heat or cook products, and more. Today, in fact, steam is used in at least one stage of the process or manufacture of almost every product we use. In order to perform all this work, however, the steam must release its heat to the product or work surface. When it gives up its heat, the steam condenses or reverts to water. If this condensate is not removed, not only does it form a barrier between the steam and the work surface, but it also reduces the heat transfer area. Initially, condensate was removed by simply cracking a valve, wasting the hot condensate and some steam as well to the atmosphere. The next step in condensate removal was the application of an orifice plate. These plates were simply discs drilled with a fixed hole or orifice. They were inserted at the steam line drip point or equipment discharge line, draining condensate and venting non-condensables from the steam space. The orifice plate had its problems, though. The small opening was easily blocked by dirt. The orifice plate was simply a fixed hole. It had no way of responding to changes in pressures or condensate load, and the wet steam discharge eroded the orifice. Over the years, many devices for removing condensate from steam by responding to changes in the system have been tried and laid aside, but each has been based upon one of a few simple principles of operation. The first is that steam, a gas, is lighter than condensate, a liquid. This difference in density is usually detected mechanically with some type of float. Another principle states that for any gas there is a temperature, called the saturation temperature, below which the gas is condensed. Traps based on this thermostatic principle use a temperature sensing element to control trap operation. The third is the thermodynamic principle, under which energy is transferred whenever liquid changes into a gaseous state. At the instant a molecule of water boils at atmospheric pressure, it expands about 1,600 times. In a confined space, this results in pressure and velocity changes. Traps that work on the thermodynamic principle are controlled by these changes. A look at present traps designed around these principles will show how they respond to various steam system characteristics. Let's start with mechanical traps, those that respond directly to the density difference between steam and condensate. The IB steam trap is a continuous drainage, intermittent discharge device that operates on the mechanical principle. The heart of the inverted bucket trap is this bucket. In the inverted position, it acts as an open float. It is capable of functioning under very high pressures because the same operating pressure is exerted both inside and outside the bucket. A small orifice called a bucket vent is located at the top of the bucket to ensure that non-condensable gases cannot be trapped inside the bucket. Steam, air, and condensate enter the trap through an inlet tube beneath the bucket. Air and condensate are discharged through an orifice at the top of the trap. At the orifice is a valve that is linked by a lever to the top of the bucket so that the valve is closed when the bucket is in the up position. The body of the trap is a cylinder which contains the bucket. During proper operation, this cylinder is always filled with condensate to a level above the top of the bucket. This condensate provides a constant water seal above and around the bucket, preventing live steam from escaping from under the bucket. Finally, in the cap of the body is a space above the water seal where any non-condensable gases which have passed through the bucket vent will collect while the valve is closed. Incoming steam is trapped between the top of the bucket and the water seal below. When approximately 2/3 of the volume of the bucket is filled with steam, the bucket becomes buoyant and floats to a point where the valve is pushed toward the orifice by the bucket clip extension. The higher condensate velocity near the orifice propels the valve into the seat, where it is sealed and held shut by differential pressure. Radiation causes the steam inside the bucket to cool and condense. If the condensed steam is replaced by more steam, the bucket remains buoyant and the valve closed. However, when enough steam has been condensed by radiation and is displaced by entering condensate so that only 1/3 of the bucket volume contains steam, the bucket loses buoyancy. As more steam condenses, the bucket becomes heavy enough to pull the valve off its seat. With the discharge valve open, condensate flows down around the bottom of the bucket and out through the discharge port. Air too rises to the top of the bucket, where it flows through the bucket vent and water seal, accumulating at the top of the trap. When the valve opens, the air is pushed out of the trap ahead of the condensate. The automatic differential condensate controller is a unique drainage device that is able to vent large amounts of flash steam and non-condensables. It may also be used wherever a live steam purge is needed to scrub the system. The DC operates under the same principles as the inverted bucket steam trap and is constructed similarly. The important difference is a secondary discharge tube which runs from the center of an umbrella-shaped shield coaxially through the inlet tube and is metered by a manual valve at its outlet. The incoming condensate and gases are prevented from directly entering this secondary discharge by the shield. The condensate forms a seal, trapping the gases inside the bucket, as with the IB. Steam, flash steam, and any non-condensables rise around the shield to the top of the bucket. The manual metering valve is adjusted to remove these gases during full capacity operation or to meet the velocity requirements for purging the system. The DC may be piped in one of two configurations depending on the job requirements. For secondary steam recovery, the discharge of the metering valve is piped to a separator and then to the top of a secondary steam header and transported to other workstations. If the flash steam and non-condensables are to be removed but not used in a secondary steam system, pipe the discharge of the manual metering valve directly to the condensate return line. At startup, steam, condensate, and air enter the inlet tube beneath the bucket. With the IB valve wide open, air is discharged through both outlet ports. Condensate fills the trap and drains through the main discharge port until enough steam collects under the bucket to float it, closing the main valve. The discharge of condensate is controlled by the position of the bucket, as with the IB trap. The manual metering valve controls the discharge of steam, flash steam, and air from the secondary outlet. Float and thermostatic traps offer a combination of mechanical and thermostatic operation. A closed float is used to sense the density difference between a gas and a liquid. The float is attached to one end of a lever which pivots inside the trap. At the opposite end of this lever is a valve that is seated when the float is at rest. Condensate enters through the inlet near the top of the trap and raises the float, opening the valve. The condensate drains from the trap through the outlet near the bottom, leaving a condensate seal between the inlet and the valve. Above this seal, near the top of the trap, is a thermostatic bellows. The bellows responds to temperature change. When this space is filled with hot steam, the thermostatic valve is closed. Non-condensables, such as air, mix with the steam and cool the space near the top of the trap. When the bellows element cools sufficiently, the thermostatic valve will open and vent these gases into a passage leading to the trap discharge. At startup, the float is down, the float valve closed, and the thermostatic valve wide open. Non-condensable gases reaching the trap are immediately vented through the thermostatic valve at the top of the trap. Condensate collects at the bottom of the trap until the float begins to rise, opening the float valve. The float valve normally drains continuously from this point. The condensate level in the trap lowers and raises the float height, thus modulating the discharge flow. When steam reaches the trap, it collects above the condensate level and heats the thermostatic element, closing its valve. Hereafter, the thermostatic valve will open intermittently to vent mixtures of non-condensables and steam. Should the trap become waterlogged, cooled condensate would open this valve and drain to the discharge line. Thermostatic traps are opened and closed by temperature changes of the liquids and gases inside them. One type of thermostatic steam trap is the bellows trap, named for the accordion-like cylinder that operates the valve. The bellows contains a liquid charge which vaporizes at or slightly below the boiling point of water. One end of the bellows is secured within the body of the trap. The valve is located at the opposite end of the bellows. When the bellows charge vaporizes, the pressure inside the bellows increases. A sufficient increase in this pressure expands the bellows to seat the valve. There are two methods of constructing a bellows trap, which determine, among other things, how the trap will fail, open or closed. In both methods, the liquid charge is added and then a vacuum is drawn in the bellows, compressing it to an internal stop. Only water is used as the bellows charge of the trap which will fail closed, and the valve is positioned to seat just short of the bellows free length. If the bellows ruptures, it returns toward its free length and the trap is closed. In traps that will fail open, a mixture of alcohol and water is commonly used as a charge because it will boil just before the saturation temperature of steam is reached. At any temperature above this point, the internal pressure of the bellows will be higher than the system pressure. With this higher internal pressure guaranteed, the valve seat for these fail-open traps is placed so that the bellows extends slightly beyond its free length to seat the valve. If the bellows is ruptured, it returns to its free length and the valve opens slightly. In either case, on startup, the valve is wide open. Any water or air in the system can drain freely through the trap. As the system reaches operating temperature, hot condensate and steam enter the trap. The bellows element is heated until its charge vaporizes. When the resulting expansion raises the pressure in the bellows sufficiently, it extends, pushing the valve into the seat. With the valve closed, there is no flow through the trap. As the condensate in the trap cools, it steals heat from the thermostatic element. Eventually, this condenses the gas inside the bellows, lowering its internal pressure. The relatively higher system pressure outside the bellows compresses it and pulls the valve off the seat to open the trap. When the fluids and gases inside the trap reach sufficient temperature, the trap once again closes. Air and other non-condensables mixed with the steam also lower the temperature inside the trap. When the surrounding temperature falls below the saturation point of steam, the charge begins to condense. With greater pressure outside than inside the bellows, it compresses, pulling the valve off the seat. The disc trap is a thermodynamic trap. These traps are operated by the energy released when the condensate changes state, or flashes between the disc and the seat. The disc trap contains only one moving part, the controlled disc itself. When the trap is closed, the disc is on the seat, sealing both the inlet and the outlet orifices. The area containing the disc is called the control chamber. It is a relatively large volume space with restricted inlet and outlet ports. It is the change of state which occurs here that normally controls the opening and closing of the disc trap. On startup, condensate at the inlet port pushes the disc off the seat and flows freely to the outlet port. Condensate passing into the trap drops in pressure. If the condensate temperature is sufficiently high to have reached the saturation for this reduced pressure, some of the condensate re-evaporates or flashes back into steam. Since steam occupies a much greater volume than condensate, flow velocity increases between the disc and seat, resulting in a pressure reduction in this area. At the same time, steam and some condensate collects on the side of the disc opposite the seat, and pressure here rises. The resulting differential pressure across the disc creates a force which snaps the disc onto the seat. The steam in the control chamber pushes on the total area of the disc, while the inlet and back pressures affect only the smaller areas of the inlet port and the discharge groove. This imbalance of force holds the trap shut. Heat radiating from the bonnet causes condensing in the control chamber, reducing the pressure above the disc. When the force above the disc is overcome by the forces below it, the disc is pushed off the seat, opening the trap and starting the next cycle. Since any gas, including air, causes the trap to close, some provision must be made to remove non-condensables from the control chamber. This is usually accomplished with a rough grind applied to the seating side of the disc, or a bleed passage machined between the control chamber and the outlet.